In our last lesson, we were reminded that a distance is always measured on the perpendicular. So if a radius is perpendicular to a chord, then it bisects the chord. If the radius of the circle bisects the chord, then it's perpendicular, which is the converse. And a perpendicular bisector passes through the center of the circle. In today's lesson, we are going to apply the relationships between congruent chords of a circle. If two chords of a circle are equidistant from the center, then they are congruent. In other words, given circle P, if PX is perpendicular to AB and PY is perpendicular to CD, where PX is congruent to PY, then AB is congruent to CD. If two chords of a circle are congruent, then they are equidistant from the center of the circle. So we're given circle O. If AB is congruent to CD and OE is perpendicular to AB, OF is perpendicular to CD, then we know OF is congruent to OE. Here in our example, we're given circle O. Segment AB is congruent to segment CD. And on the diagram in your textbook, it's marked that OP is perpendicular to AB and OQ is perpendicular to CD. So even though it wasn't directly given in the textbook, it is marked on the diagram, therefore we know that to be true. So I'm going to mark the diagram, and now I see I have congruent chords. If the chords of a circle are congruent, then they are equidistant. So now I can say that OP is equal to OQ, and then substitute the algebraic expressions that they gave me. If I subtract 4x from both sides, I get 8x minus 5 equals 19. Now add 5 to both sides, I get 8x equals 24. Divide both sides by 8, I get x equals 3. Therefore, OP is equal to 12 times 3 minus 5, or 36 minus 5, which is 31.